Hello everyone. Today's video is about the inverse matrix theorem, but before we get to that very important theorem, we'll talk about how to find and compute inverses of a matrix. What we know so far about inverses is that not every matrix is invertible, but we know a very special set of matrices that are a very special class of matrices that are invertible, elementary matrices. So the next result, which is going to be the first theorem for today, is a criterion, a condition to know whether a matrix is invertible or not. In fact, the theorem says that a matrix is invertible if and only if its row-reduced echelon form is the identity. Let's try to look into why this theorem should be true. Well, one arrow of this implication, this if and only if, we've already explored. If the reduced row echelon form of the matrix is the identity, then by the previous theorems that we saw in the previous videos, there's an invertible matrix P such that we can write the identity as P times A, and P is invertible. In other words, by multiplying both sides here by P inverse, we get that A is nothing but P inverse itself, and the inverse of an invertible matrix is invertible. So A is invertible. Let's suppose the converse. So let's suppose now that we know that A is invertible. We want to show that its row-reduced echelon form is the identity. A is a square matrix. So since it is invertible, let's check for solutions to AX equals 0. But since A is invertible, I can multiply this on both sides by A inverse. But A inverse times the 0 vector is nothing but the 0 vector. So this tells me that X is equal to 0. In other words, the only solution to AX equals 0 is that X itself is 0. This, by a previous result we saw in class, is equivalent to saying that the columns of A are linearly independent. But if A has linearly independent columns, then its rank is equal to n, and the number of pivots it has is equal to n. However, since A is a square matrix, the only way that you can have n pivots in A is that every column is a standard vector, one of the following ones, and so on. So when you are done with your matrix A, reducing it to echelon form, what you are left with is actually a copy of the identity matrix. So I'll draw a big 0 to signify that there's all zeros there, and another big 0 down here to mean the same thing. It's all zeros except for on the diagonal, because the columns of A, the pivot columns of A correspond to standard vectors. In other words, A is indeed equivalent to the identity under the row-reduced echelon form. A simple consequence of this result is that we can't have matrices that are that are in squared. Matrices that are in squared cannot be invertible. If you think about it, you cannot have the correct reduced row echelon form for matrices that are in squared. You can't get the identity by reducing a matrix that is in squared. The next thing we're going to focus on is how to compute the inverse of a matrix. So now we have a good way to detect whether a matrix is invertible. When its reduced row echelon form is the identity, we'll know it's invertible. The next question is, how do we find the inverse? Well, the idea that we're going to use to find the inverse comes from what we did to solve linear systems. To solve AX equals B, we used elementary row operation to boil it down from the augmented matrix AX and B to the reduced row echelon form of A and some other vector B prime. Now, we no longer want to solve ax equals b, but we still want to solve some sort of equation, which is a times its inverse, which we're looking for, equals the identity. So we'll use the same principle. Instead of augmenting a with a vector b, we'll augment it with a copy of the identity matrix, and we will get something by performing row operations to that. When we reduce to the reduced row echelon form here, two things may happen. If A is invertible, then its reduced row echelon form is the identity. And so the scenario that we put ourselves in is that the reduced row echelon form of A next to the identity will be identity next to something. In this scenario, that something, that vector C, that matrix C, is the inverse of A. So that's how we compute it. If the reduced row echelon form of A is not the identity, then well, this method will break, but that's fine because in that case, A has no inverse. So there's no chance that we can compute one. Let's try this in an example. We don't know whether A is invertible, but we look for its inverse. And to do that, we do the following thing. So we stick an identity matrix of the same size next to A. And now we perform Gaussian elimination on this first side. We have to carry along all of the rows, but we'll do the operation to reduce the first side to an identity. So here are the operations I'll do. The second row, I will subtract 3 times the first. So I get 1, 2, 3, 1, 0, 0. And here I get 0. 9 minus 6 is 3. 15 minus 9 is 6. Negative 3, 1, 0. And then here I'll subtract twice the first row from the third. And I'll get 2, 2, minus 2, 0, 1. Okay. Let's proceed to the next step. Maybe I'll do the following. I like the third row better than the second, so I'll move it to the second slot, and I'll divide everything by 2. And my third row, I could divide it all by 3 to make it simpler. Okay, now I want to eliminate my entry 1 here. So I'll have to eliminate these 2 entries. Let's do that. So the next step here, we'll see instead of the first row, I'll put itself minus twice the second. So we'll get 1, 0, 1, 3, 0, minus 1. That's what I get by minusing the second row into this. The second row won't change. 0, 1, 1, minus 1, 0, 1/2. And the third row, I will replace it with itself minus the second. I'll subtract the second row from the third. So I get 0, 0, 1, 0, 1/3, and then I have minus 1/2. We are almost done. Remember that our goal is to make the first half of this big matrix into an identity. To do that, I will add the third row to the first, subtract. And I will subtract the third row from the second as well. So when I subtract the third row, I get 3 minus a third and minus 3/2. When I subtract it from the second, I get minus 1 minus a third, 0. And the third row is 0, 0, 1, 0, 1/3, minus 1/2. Okay, so we can read off our result from here. The matrix A inverse is the 3 by 3 matrix whose entries are 3 minus 1, 0, minus a third, minus a third, a third, and minus 3/2, 0, minus 1/2. That's how you compute the inverse of a matrix. Now we come to the big theoretical theorem. It even has a name, the invertible matrix theorem. This is a theorem that lists equivalent conditions for a matrix to be invertible. We've seen some of them we've seen today, some of them we've seen in the past, but we'll recollect them here. So all of these statements are equivalent. Let's just go through them. A is an invertible matrix. What we saw today is that that's equivalent to having a reduced row echelon form equal to the identity. But if that's the case, then the rank of A is also equal to its size, n. If the rank is equal to n, then the columns of A are linearly independent, so they span the whole real space Rn. If the columns span the whole real space, then the equation is always consistent no matter what B is. But then if the rank is equal to the size, the nullity is 0. So you see that we're saying the same thing in many different ways. That's useful. That's how we make progress in the theory, by tying together different concepts. Again, if the rank is n, then the columns are linearly independent. Linearly independent columns means that the equation AX equals 0 is indeed equal to 0. I and J are existence of an inverse matrix. B and C are matrices that are inverses on the left or on the right. And K is maybe the most surprising one, but it shouldn't. A is a product of elementary matrices. So all of the matrices that are invertible are products of elementary matrices. The reason why this K is true is the usual. If the reduced row echelon form of A is the identity, then there's an invertible matrix P that writes this equation here. Then A is the inverse of P, but I remind you that P comes from elementary matrices. Okay, let's have a look at a couple of consequences of this theorem. There's a couple applications that I should mention at this point. One is a way to compute A inverse times any matrix here. So this is some sort of elaboration on the algorithm that we used above to compute inverses. The algorithm we saw was that if you start with A and the identity, then you do a reduction to row echelon form and you get the identity and A inverse. What happens if I start with a matrix B instead of the identity? Well, the claim is that what comes out of that is that you'll find A inverse times B in the second slot. Why is that true? Well, the reason why this works is the following. We have that row operations, again, correspond to our matrix P. And by what we just wrote, P inverse is equal to A. And P well, P is equal to A inverse. Let me write it like this. But then the same row operations transform B into K. So PB is equal to K. If I merge these two things together, I get that PB, which is equal to K, is also equal to A inverse times B. In other words, the result K here is A inverse times B. Let's do one example of this. So to compute A inverse B in this example, what I want to do is to set myself up as if I was computing an inverse, except I don't add an identity matrix in this second block. I will add the matrix B. And now we try to reduce to the case in which the first block in this matrix is the identity. So we can do that by subtracting twice the second row to the first. And we get 1, 0, 1, 0. I subtract twice the second, so that's a -7. 0, 1, 1, 1, 3. Nothing changes there. And then I subtract twice the second row from the third, which gives me 0, 0, -1, -2. And then I have 2 minus 6. That's a -4. Allow me to change the signs in this last row. That will make our next step a little bit faster. So for the next step, I'm not going to write what I do, but I will subtract the last row from the first and from the second. So in the first row, I get 1, 0, 0, -2, -11, 0, 1, 0, -1, -1, 0, 0, 1, 2, 4. And you are welcome to check that A inverse times B is the result of this algorithm. In other words, it's -2, 11, -1, -1, 2, 4. Let me mention briefly one other application, after which this video will be over. This application here concerns the following question. Suppose I give you a linear system, AX equals B, and now I make changes to B, just a little bit. I perturb B, and I want to know how does that affect the change in my solution X. Well, the setup that we could use is the following. For example, let's suppose that I take my vector B, but then I perturb it by a small scalar multiple of a standard vector, k of A1, k times E1. Now, suppose that V is a solution for AX equals B, and U is a solution for AX equals B plus K E1. And let's compare U and V. Here they are. Well, by multiplying everything by the inverse of A, I get that from here, V is A inverse B. And from this other one, I get that U is A inverse B plus A inverse times K E1. But now, well, A inverse B is equal to V. So, so U is V plus a little piece. So what this little piece is the following. This is K times A E1, which I will call P1. This A times E1 is the first column of A inverse times E1 is the first column of A inverse. So if I write A inverse as it's written here, P1, P2, all the way up to Pn, then A inverse times E1 is exactly my vector P1. So the upshot of this is that if I perturb B by some standard vector, scalar multiple of a standard vector, the solution to the linear system moves by the same scalar multiple of one of the columns of the inverse matrix. This wraps up all of our discussion with inverse matrices.